Velsanet's second white paper defines wired-wireless convergence. The core idea is simple. Wireless is not a network. It is an entry point. A wireless signal maps into the optical layer 1, and from that moment, the optical core becomes the network. The signal is received at the radio unit, then immediately mapped into an optical core. From there, Velsanet's optical layer 1 handles everything. Wireless only determines how the user reaches the core. All network behavior begins after optical mapping, and this paper describes only that mapping. Each wireless device maps to one optical core. It's individual end-to-end, composed of 8 internal channels. These are not separate cores. They are lanes inside a single core. The first channel is always reserved for device monitoring, topology awareness, and end-to-end creation signaling. The first channel is the control lane that makes the core self-aware before any user traffic flows. It continuously monitors the device, tracks where the core sits in the Velsanet structure, and carries the signaling, called TCC, that requests and sets up the individual end-to-end path. The Velsanet Mobility Convergence Unit is not part of Velsanet equipment. It is an external module that coordinates the wireless domain, and it does only 3 things: manage individual end-to-end, create parallel end-to-end, and sequence mobility. It controls, the equipment only executes core activation. The V-MCU keeps the record. It tracks which device uses which optical core, creates and releases individual end-to-end paths, and maintains the mapping tables that mobility depends on. This device-level bookkeeping is the foundation everything else is built on. Parallel end-to-end is simply multiple individual end-to-end assigned to the same device. The device requests it, the V-MCU finds the next available optical core and commands the equipment to activate it. Parallel end-to-end is nothing more than a repetition of individual end-to-end. Handover works through overlap. The existing end-to-end stays valid, while a new one is pre-created in the target cell. Once the new path is stable, the old one is released. No packet loss, no PHYMAC handover complexity, no rerouting. The user simply moves. Its scope is deliberately narrow. The V-MCU does not handle intercity routing. That belongs to the dodecahedron D12 and icosahedron I20 nodes. The network AI, it does not control optical switching matrices, does not manage wired-wireless synchronization, and does not optimize high-level traffic. Its only job is device-level end-to-end. The access layer is 3 polyhedral nodes. Tetrahedron T4 is wired access. Hexahedron H6 receives both the wired T4 and the wireless RAN. This is where wired and wireless converge. Octahedron O8 hosts PAI and EAI. All 3 use identical optical core resources, keeping behavior deterministic. In summary, wireless provides access, and the optical layer 1 becomes the network. Individual end-to-end equals one core, parallel end-to-end equals many. The V-MCU handles end-to-end, parallelization, and mobility. Global routing through the D12 and I20 nodes stays entirely separate. Isolating wireless complexity guarantees deterministic behavior in the optical layer. This wireless-to-optical mapping is a structural framework. The detailed mapping rules, modulation alignment, and hardware integration will be finalized through real hardware testing. Once the Velsanet Research Lab is established, the architecture is set. The implementation follows the lab.